It's not algorithms, it's not data, it's not compute. Everybody is basically misleading you actively. It's the humans who have to implement these things. The latency for flash attention, the original flash attention, to get adopted was well over a year. We want to find the bottleneck, the search space is too large. So that is the punchline. I'm Manoj. I recently joined the AMD AI group. I'll just go on for a minute about my background so that you know if you can choose if you want to listen more to me or look into your phones. Hopefully the former. So I recently, a few months ago, I joined AMD AI group. It should be obvious, AMD AI group. Before this, I worked at Perplexity AI, where I was leading the inference team. Large-scale models, handling a lot of traffic, search traffic. And before that, I used to work at Tesla Autopilot, where I was working on the full self-driving system. I also got to work on Optimus robots back when Optimus was still not a thing yet. It was just a metal hung from a gantry. Basically, it kicked me and my manager in the shin, and we both, it was basically the homing reset position was awkward enough. It was just a bunch of aluminum just kicking us. From those days, I worked on it because I was working primarily on inference, onboard inference. I had the sort of fortune to work on both FSD and Optimus because Tesla uses the same ASIC for both FSD, the autopilot fleet, and the Optimus robots. I'll ease into the talk, but basically, before that, I spent some time in AWS AI ecosystem, where I worked sort of closely with PyTorch team, so that was kind of lucky because PyTorch was not a thing yet. It was just coming out of the cafe mode, and TensorFlow 2 was not out yet, and MXNet was a thing, stuff like that, and ML compilers were like the next big frontier. So the models were pretty much as big as a BERT. BERT was still new. We're like, oh, whoa, WTF, what's going on? That's kind of my background. But before that, I spent a lot of time in the lower levels of the stack. I worked on things like, smart home robots, but really, I worked on low-level Linux kernel development also, which was my primary goal in life, right? So I wanted to just get a couple of commits into Linux kernel, but then got that done too early. So then I was like, okay, whatever. Let's see what smart home products are, etc. So I worked on the original Alexa, the cylinder. Then I worked on a bunch of other related Alexa products and home products. Okay, that's it about me. You can choose what you want to do next. Yeah, that was hard to get through because I don't like talking about myself, but I want to talk about this. So the background to this is anybody on CUDA mode was on CUDA mode, GPU mode. I like the T-shirt. I was actually thinking of wearing that. I have the T-shirt at home. Yeah. So CUDA mode is this amazing resource if you are interested in things like writing optimal GPU kernels, or actually the who's who participates. You can really ask questions. Andre Karpathy used to be on the Discord channel. It started off really as a YouTube channel and Discord channel, and things like people like Andre Karpathy, TreeDAO are there. If you're even remotely interested in the domain, you'll probably have heard of it. I'm surprised only one person. I'm hoping others are just shy. Okay. Yeah, so they have an IRL meetup. So the V1 was last year when Andre Karpathy was there, and he gave that famous talk about how to think about LLMs and software 2.0 and 3.0 and stuff like that. I participated there. I didn't quite compete. I just went there. I didn't really think of. I was just I was just happy to be there, really. So this year I had a little more, forethought, I guess. So even then, I did not prepare. I just went there and started asking people if they were interested. That was my preparation. But this topic definitely interests me. So let's get on with this. Yeah. It's not algorithms. It's not data. It's not compute. Everybody is basically misleading you actively. It's the humans who have to implement these things, right? I mean, we'll get to what the question is. These are the answers, right? Like Elon says, or Hitchhiker's Guide to the Galaxy. It's not the answer, really. It's like really the question. I think the answer is really the humans who have to implement these things, whatever these things are. So pretty much the latency for flash attention, the original flash attention, to get adopted was well over a year. Why? Your guess is as good as mine. But it turns out to be like, for things like VLLM or SGLang and others to truly adopt this, it was like very long. So we want to find the bottleneck, right? Let's take a step back. So you guys are probably expecting like, oh yeah, AI is going to just discover everything, AGI, ASI, it's going to do everything of everything. We'll get there, but we'll have to go through some painful stages. These can be some of the painful stages. So what does an AI researcher do? You guys are probably better equipped than me. I'm more on the engineering side. So we read through papers, tweets, Discord channel, talk to each other. I just overheard a very nice discussion that somebody was having about mechanistic interpretability and logic lens, and I totally agree. In fact, somebody was exactly mentioning what this is about. Not every paper, or there's no set of magic papers that you just read and become, yes, Ilya's, or the famous 39 papers or whatever, I forget the number, where, John Carmack famously asked Ilya Sutskever, what are the papers that I need to get to become competent? And I think Ilya Sutskever shared like some 31 or 39, I don't remember the exact number of papers, but that was going around. So if you thought of that as a basic syllabus for reasonable competency, it's not really expertise. That's the important bit, right? So how do you guys become experts in whatever sub-domain, niche, topics that you're interested in, right? You're usually passionate about things. You're usually curious about things. And it's not like some sort of like this idealistic view. You're just like curious. Oh, okay, I was just like remotely interested in mechanistic interpretability, and the logic lens thing caught my ear. That's really like in a nutshell, that's really what happens, right? You read through papers, you overhear people, and it's not possible to capture all kinds of conversations at all times, right? With that said, our attempt the project I'm going to talk about was not just like, we did some kernel evolution, optimizing GPU kernels through some LLM-based systems in the GPU mode hackathon. Then I also did the extension version of this in XAI hackathon, which was like last month, where we ended up adding, so they gave us like access to X's APIs, where you can actually read through threads that people share, conversations, different posts, etc. Right? So, which is really a goldmine of information. So, and you can't always capture all the essence. So you're like, okay, that's really what an AI researcher does, especially in high signal accounts. Like going back to Andre Karpathy shares a tweet or shares a paper and talks highly about it, I'm going to probably read it, or we're all probably going to read it, right? That's the general idea. So what we ended up doing was we used the XAI's or X's API, and we would sort of give it like some set of venerable X accounts, respectable accounts that share these papers and stuff like that. So the idea was read papers, generate ideas, and not stop there, but optimize kernels if possible, right? That's the hard part, right? So what if we could like automate this entire pipeline? It's a lofty claim, but you're done, right? You wipe code first stage, you wipe code second stage, and you're done, right? No, it's actually not quite. This is the famous meme. I'm a bit of an AI researcher myself. Not really. If you think about it, if you play with the idea more seriously, what this actually enables is, if we are able to actually have LLM-based systems generate kernels that run optimally, what it does is think about it this way. Today's LLMs make tomorrow's LLMs run faster. That's not the case today. Today's LLMs give some sort of like, synthetic data for next generation's LLMs to become better at the evals, right? That's really mostly what they're doing today to improve future AI. But if we are able to allow sort of think about this self-improvement hypothesis, what we're effectively doing, again, this slide was directly from the XAI hackathon, so there'll be Grok, but you can replace it with any LLM. The idea is that today's LLMs will be able to generate kernels that make future LLMs actually run faster. When I say faster, I mean latency and throughput and stuff like that. All the system metrics included, okay? Feel free to ask any questions so far. Should be straightforward. I've not gotten any. Oh, no. Yeah, okay. So this was a 36-hour hackathon, I believe, 30 odd hours. So within the 30 odd hours, we were able to magically get like 27% speed up on a very tiny model for a longer context length. This is embarrassing, but the funny thing is, I want to keep this because this is how raw the competitions are. You're just like sleepless for 30 hours. So this is not like a grand NeurIPS award-winning paper or something. But within 20 hours, can you achieve something actually reasonably useful, right? So this is our actual result. What happens is, what did we do? We selected parts, basically attention. We asked whatever system I'm going to describe next, LLM-based systems, to generate parts of attention kernels more optimally for some definition of optimal. In this case, the definition was forward speed, right? We run it through, we run the forward pass on the models, and we plug that attention mechanism into all these different models. Actually, there are more. We can go into that in a bit. But we actually find speedups, right? So that was this is the actual graph. We had like a whole bunch of LLMs. And this dashboard, I believe, I just have one of the participants, one of my friends, wipe coded the dashboard, but the hookups are all real. They're all backed by real server. I'm happy to share the link later on. But question?
Like I have a question.
Yeah, please.
So, I mean, you got speedups here, but then like a fair question might be, the speedups might not be as significant if written by someone who's making understanding of the chip architecture of the kernel.
Absolutely. Yeah, that's a good question. We'll come to that. Exactly that. Yeah.
So currently we are doing only training or including it?
It's the speedups we had time only to plug into forward pass, but they're literally the same kernels that go for the backward pass as well. If you thought of some poor man's version of training is both forward and backward pass, that's basically, it should apply to both, right? So we did not have the time to measure the training times, but it should apply.
And do you have access to the hardware that it's going to run on?
Yeah, we just selected, okay, I didn't realize. It's right here. We just selected NVIDIA B200. I know. I'm supposed to be I'm supposed to say MI350, AMD. It is good, but I think we just had access to this at the moment, so we just did that.
Also, when you said you put this into LLMs, what was the LLM actually? Is it?
It's a Hugging Face model that we download,
okay.
right? The transformers.
What is optimizing it? What's?
Yeah, coming to that.
Yeah.
Well. So, what is optimizing? Yeah. So basically, we went through the whole. I think I covered most of this. Basically, how do you go through? Going through archive was like drinking out of a fire hose, but it's also very slow. How often do people share there, right? And so on. So that was a thing I wanted to share. All right. I'll get to the crux of this. The pipeline was effectively like this, right? So fragmented knowledge. What we do is the font clear? It's super unclear to me.
No, it's not.
Not clear? Sorry. I'll share the slides offline, but I'll just try and walk through this. Yeah. The data flow here is that they're like basically fragmented knowledge, and how do you go about it, right? So you can use semantic search. I have EXA semantic search, they should say. EXA is just a an API. It's a very good API, but it basically just performs semantic search based on like some sort of vector embeddings match, cosine similarity, stuff like that. The usual stuff, I guess, for the most part. Distance metric and stuff. And then we also use search on X, like I mentioned, right? So we combine what we did for the scope of the hackathon, but if you're continuing this idea in your actual research, in a real world research, you don't need to be limited. What we actually did was we select a topic that the user is interested in, and we have like dedicated set of sources, such as, like I said before, allow listed or whitelisted set of X accounts that share papers, and archive top X number of results, I forget, like top 25 results or whatever. And then we pass that as the context for LLM context synthesis. What is the idea here? We want to like think of it again like an AI researcher. We consume this research. This part is where they're reading through different literature, and then there's an idea generation phase. Right? How do you go about that? That's the hard part, right? So what is novel? So we allow LLMs to sort of decide what novel is. In this case, we just asked Grok 4.1. We had access to that. We were given like sufficient credits. But if you have like a council of LLMs, it works better, we found. So we threw in Opus and GPT 5.1 at the time. So you end up getting better novel ideas, and you can have them vet each other, the usual stuff, right? You can have like separate dedicated LLM reviewer, etc. Again, I'm not yet gotten to the part of kernel generation. This is just the research, literature consumption, and stuff like that, right? So you have these novel ideas, and we can actually validate them in the sense like at a high level, we can ask one LLM to review it and kind of trash talk about it. It's actually fun. That phase is a lot of fun.
Yeah, so this extra search stage, couldn't you have just used the deep research parts of the LLMs?
It's the same thing. It's just that deep research is, you can't always control the sources, right? That's fair. You can do that. It's just different set of sources. That's still, it's fair game. Yeah, but the idea is, are you able to generate enough? The idea is, are you covering sufficient number of sources that you are happy with? Because you can't consume all of it. And then are you generating reasonably good ideas out of them? Because if you look at it, the number of new ideas kind of taper off as you consume more and more papers, because they're all pretty much saying the same fundamental core principles in them. Okay, so then we come to the idea generation, and we wanted to do this with structured outputs, right? So we used DSPY. I'm just going through the stack so that you get an idea if you want to replicate this. Some of this is open source. I'm happy to share them offline. Actually, most of it is open source. I'm happy to share them offline. And happy to collaborate with anybody who's interested in taking it further. So the idea here is semantic search, and then kind of this weird open-ended search in X or any other social that you prefer. And then LLM synthesis of ideas in a structured output, so that you can have a proper evaluation of these and proper reviewing of these. And basically, the core principle of this is you're getting these ideas like sort of in words and tokens, which is kind of weird. But what you're not getting is the actual like arguments, like actual kernel parameters, kernel configuration parameters, or things like that, right? So you just get these like, okay, attention, paged attention might be better, and so on. So, but we're still in good place, because Claude or Grok 4.1 or so on are amazing at generating PyTorch code, right? Which is what we wanted to make use of. So we ended up generating PyTorch code. I'll come to why not something else, right? Because kernel generation is good only in certain languages, okay? If you try to generate CUDA or HIP C++ kernels, you'll end up having a very torrid time. You need to have your eval and benchmarking loop will become just very time consuming, let me put it that way. It's actually much more harder. You get syntax wrong, God forbid you have like, you miss a star in the C++, in C pointer, or you miss any dunder qualifiers, you mess up any sizes, you don't static const expr something, you're kind of like screwed in a lot of different ways. You don't want to find out during the LLM iteration. So what we ended up doing is we want basically a DSL of sorts that is very definitive, very specific, very almost over-specified if you want, right? We want the code generation to be as close to PyTorch as possible. Can we find that, right? So that's really, but before we go there, LLMs cannot generate optimal code, let alone they can't generate like usually functioning code, let alone optimal code. Why is this? There are different hypotheses. You guys might be better judges here, but I think severely undersupply of training data. That's one obvious problem, but I think there's more to it because, like I said, the syntax, again, can go back to training data, but you'll end up specializing these beasts, these shoggoths, for some weird syntax, which is probably not worth it because it's such a niche case, right? So you don't want to try and supply enough training data in the hope that you'll always get optimal kernels, because what are these kernels? They're basically trying to implement some mathematical operations, right? So you don't want to try and hyper optimize in that weird DSL for some arbitrary unknown convex optimization in the future. Okay, so hopefully you guys know. I'll get into some detail. I might skip a bit of the gory details of I wanted to cover alpha tensor, right? Okay, refreshed memory, right? Things like, for optimizing kernels, it's not very obvious from the beginning, right? You need to be aware of the hardware constraints. First of all, hardware specs, then the constraints. You don't want to have like vector VGPR spillage, things like that. Or you don't want to have, generally you don't want to have register pressure. You have only certain amount of memory that you can fit all the vectors and all the tensors in. So, for example, bear with me. I think you'll probably enjoy this if you're the right type of crowd. Multiplications are more important to optimize than additions, or not optimize, eliminate multiplications when possible, right? As obvious as it sounds. I hope it's obvious. If not, multiplications are more expensive in the hardware circuitry because effectively multiplications are additions in a loop, right? If you break it down to first principles. So there is a, asymptotic impact on having more multiplications. For example, let's take CPUs, right? CPU, if addition takes 1 cycle, scalar addition, scalar multiplication can take up to 20 cycles. And this is already in an older CPU. I'm ignoring all the vectorized instructions, all that stuff, right? Just the spirit of it still carries over to GPUs as well. It's just that we do a lot of these in parallel in GPUs, right? But just if you don't learn anything else, just learn that, one of the tricks to speed up any matrix multiplication is to eliminate multiplication and try and substitute them with additions. I'll not go into this, but fundamentally, I'll give you a very hand-wavy description, but there are better resources than this slide for you to go through. But fundamentally what this is I'm describing how Alpha Tensor tried to solve this. This is Google DeepMind's. Anybody from Google DeepMind here? I know they have like an office in Bangalore. Okay, but nonetheless, what they're doing here is for any, let's say, n by n matrix multiplication, they actually represent this. So the idea is you want to get optimal multiplication computation, right? Like I said, in the optimal case, you have as few multiplication as possible. So what they do is how do I explain this? For let's say 2 by 2 matrices multiplying, right? So effectively, what happens is Strasson's algorithm that was the most optimal algorithm until I guess like something like late 1960s or whatever. So it stood the test of time for 50 years. Basically, that was like the most optimal, and it effectively reduced. Yeah. So basically, let's say let's leave it there. Yeah. So what effectively alpha tensor does is you have to decompose a tensor into smaller matrices, and effectively, or in essence, alpha tensor gamified this so that they could apply RL on top, because they were so good at like solving games through RL environments. Effectively, they kind of like gamified this for the algorithm, for the RL, and that's how they were able to discover new ways of achieving the same matrix multiplication, optimal matrix multiplication algorithm that was previously not found because the search space is too large. I think I've said in different words these things, but this is the Strasson's algorithm and some aspect of why it works. It's interesting, but it's not, yeah, you guys can take a look at this offline. I think you'll enjoy it if you go through the whole paper. There's a whole Nature article. Effectively, they, like I said, they take the 2 by 2 matrix and have it as a 3D tensor of 4 by 4. 4 by 4 by 4. Basically, n by n matrices are represented as n squared by n squared by n squared 3D matrices, 3D tensors. Okay, let's get to the meat of it. Yeah. So, going back to our project, why was that interesting? You can now understand what sort of things to think about to optimize kernels, but it's not all free, right? You can't just expect LLM to figure this thing out unless you guide it very carefully. And even if it is a single LLM, you can't get this done. It has to be a council of LLMs. Okay, so Python now speaks GPU, right? Like I said, there is Helion, which is basically, it was announced recently in the PyTorch conference. It's effectively, think of it as like PyTorch with tiles. And then there's TileLang, there's of course Cutlass DSL, there's one coming up from AMD as well. Actually, it's been in the works, it's just not, I guess, like announcement ready. It's called Wave. And I'm sure there are a whole bunch of boutique DSLs that are available where you can express your GPU kernel implementation as a DSL, but it's Pythonic, only in the sense that it seems like Python. You just say Python interpreter, but there's a whole bunch that happens. We'll cover that, yeah? But the fun is that somebody asked, Python, GPU, this is a great gateway for us, right? So, yeah, actually this is perfectly murked. Helion has 30 lines of code, and Triton has like several lines of 4x, 5x the number of lines of code. Why is that relevant? Because effectively, Helion is nothing, Helion is like Triton plus auto-tuning. Who's familiar with Torch Compile? Has anybody used Torch Compile? Okay, good. Oh, wow, okay, good. I expected fewer. This is good. So Torch Compile, effectively what you do is like, you apply different options. By default, you might just say Torch Compile on a module and expect it to work its magic, which it does for the better part. But the actual secrets are, if you set max auto-tune, what it does is it actually performs something called auto-tuning. Any compiler nerds? Basically, auto-tuning is this mechanism where a certain set of configuration parameters for this can apply to any programming language. This is just a general compiler thing, right? So if there are a bunch of different configuration possible of running a specific operation, the compiler in the backend tries to search for it, which is really what Helion is also doing. So what I would have probably expressed here is, we'll come to that, but there are things like block sizes, strides, indices, a whole bunch of these parameters, tile sizes for a given kernel in PyTorch that are applicable, but you don't see it, right? Unless you override it or have Torch Compile specifically look into it, right, through specific voodoo options. But Helion kind of tries to eat that away and allow you to run PyTorch code, but you can also specify the types of configurations that you want it to explore over. That's really, I mean, Jason, who's the author of PyTorch, Helion, is going to be mad at me, but that's really fundamentally it. It's lots of lipstick, but Triton plus autotuning plus lots of lipstick. But the great thing is, it eliminates the syntactic and semantic harassment that we go through if we ask LLMs to generate CUDA code or HIP code and so on, right? So it eats away because LLMs are already pretty good at generating PyTorch, yeah.
I'm not sure about I'm not familiar with Torch Compile, but it sounds pretty similar to JAX. So is it?
Yeah, JAX is a fundamentally compiled language, you can think of it. Yes, it's Python, but I love that you asked this because JAX it's backed by a static compiler. Its OpenXLA system is fundamentally an MLIR-based compiler infrastructure, which lowers the high-level representation of your computation. JAX is like NumPy. It's basically NumPy, right? So what they ended up doing was express NumPy, but it's optimal for your hardware. In their hardware, it's weird, like TPU, ASIC hardware. But we did this, and we didn't do JAX and Tesla, but we did something very similar, but we used PyTorch. We walked through, we captured the graph, and then we built effectively what eventually looked like OpenXLA internally. And it's MLIR based. What MLIR stands for is quickly multi-level intermediate representation. It has nothing to do with machine learning, but the intermediate representations are the key part. It is originally written by Chris Latner and a bunch of others. Bunch of others work with me in AMD right now. They're great people. Very, very exciting, very smart people. So if anybody is interested in talking to them, happy to connect you guys. But going back to JAX, if it effectively lowers it to different intermediate representations like stable HLO and so on and so forth. There's vector dialect. So the idea is each of these dialects have their own advantages as to what sort of optimizations you can apply on them. Okay, such as there's something called tensor semantic and buffer semantic in MLIR ecosystem, where certain dialects is basically a bunch of collection of operations and types. Think of it that way for non-compiler people, right? It's just this specification of types and operations, but as you're lowering, right? What are you representing? What are your operands and types of, right? So in tensor semantic, this can be represented as just these mathematical functions, f of x equals x plus bar, right? So x can be tensor, x can be scalar, x can be vector, whatever, right? So you don't care about it at that level. You just care about the mathematical operations. And then as you lower them, you start caring at some point about, oh shoot, like what is the buffer semantic about it? How much do I allocate? Where do I allocate from? What is the data type? Which, is it from GPU domain or DRAM domain or things like that, right? So JAX, you're right, but Helion has its own set of compiler technologies, which is Triton-like, right? If you're familiar with Triton, it uses the same compiler technology, which is, again, even Triton is also written with MLIR, but MLIR, think of it in your mind as LLVM, right? It's like an infrastructure to writing compilers. It's not a compiler itself. Like Rust is built on MLIR. Clang can be used with MLIR. Oh, sorry, I misspoke. Rust is LLVM and C compilers Clang with LLVM, but similarly, OpenXLA is built in MLIR. Similarly, Triton is built with MLIR ecosystem and stuff like that. So they all have their own intermediate representations that are defined, and you can lower to those. So that's the idea I was trying to convey. Okay, in that sense, it is like JAX, but it is not JAX, right? So, that question? Okay. So going back to this, so Helion has this advantage where it effectively introduces this automatic notion of tiles to PyTorch. And going back to why this is relevant to you guys, when I say guys, gender inclusive, sorry. LLMs are great with generating PyTorch. So how do we sort of hook our thing into this where we can optimize these kernels? That's really what I'm getting at, right? So the config space that we just discussed, right, it can get very massive. Actually, this is exactly, I forgot that I had a slide exactly for your answer, for your question. So let's go through this. There's Triton IR, then TTGIR, GPU specific Triton dialect, then LLVM IR, which is the generic intermediate representation for all LLVM code. From here, it diverts into the hardware specificness, where it can go to PTX assembly in NVIDIA code, or AMD GPU binary assembly for AMD GPUs, or in case of TPUs, it can go into whatever weird thing they have as well, right? But the idea is there's optimization passes at each stage that are relevant and applicable at different levels. And I apologize that the resolution is crap, but I'll share these slides offline so that you guys can take a look. Yeah.
So how do you decide these abstractions that you will generate? So you generate like LVM or GPS?
This was just for illustration. What we are generating is at the highest level. Good question. There are, in fact, I have a PR in OpenEvolve. By the way, the whole alpha evolve thing that I will eventually get to, let me know how we're doing on time, Alpha Evolve is this Alpha Star series, right, from Google DeepMind, all of which are breakthroughs, amazing, etc. But we don't have open source version of Alpha Evolve. Exactly. So that is the punchline. So one of my friends implemented OpenEvolve, and I was like super happy about it, and it's already quickly become famous and like popular with lots of applications. And one of the examples, you can go to the example section there, you'll find attention example. I wrote that for one of the IRs, I forget which one I was writing, maybe vector dialect or one of those dialects, Linolge dialect, where we're trying to optimize only in Linolge dialect and then lower it, then do rest of it, let the compiler do the rest of it to convert it into binary, right? Here we're not doing that. Here we want to stick with PyTorch, because remember our goal was, ideate, consume this whole X stream, archive papers and all that crap, and then we can't emit an LLVM IR. It's too cumbersome for an LLM to generate coherent IR for LLVM, right? So we emit PyTorch. Now we back it up with these dunders and qualifiers for Helion expressions, where we say, hey, these are the configs that are relevant to this kernel, explore on this, okay? That's why this is relevant. And why did I put this? This is Helion's compilation pipeline to say that there is nothing great, right? It's not some magic. It is literally doing Triton, right? It's just literally doing Triton over large config spaces. You can also think of it as like somebody asked, torch compile with larger config space, right? Search space. So what gives, right? Helion should solve everything. Everybody has written their code in PyTorch, right? Done, right? Anybody wants to take a stab at what's possibly, what's possibly the downside, if you will? I mean, it's great, it's fantastic, it's just new, it's out of the oven. So if you want to help, please go ahead and make your PRs in Helion. But with what I have described, right? It's basically PyTorch with configurations for specific kernel parameters like block sizes, strides, and all this crap that I talked about. So, right? It's magic solution. Everything is done. What's missing?
And you don't know the actual configs at compile time or runtime. What chance the best?
Let's say if I give you the right config spaces, right? Config parameters, and if all I'm asking Helion to do is, dude, one of this combination is optimal for me, for my workload, just go find it. What gives? Somebody else said something.
Said communication overhead is not part of
Config space.
Okay, let's say, okay, fair. I'll limit it to only a single node. Let's say I don't care enough about like communication yet. And remember, these are all happening offline. Right? These are not even during the runtime. Well, there is an option to do JIT, but let's say we're doing AOT because we care ahead of time compilation. Like, you have C code, you compile it, and then you emit binaries and you run your a.out. That's the ahead of time compilation, where compiled versions are generated ahead of time.
So how are you defining the objective function?
Let's say in this case, it's just the latency or throughput. Fair question, but typically Helion in their blog, optimized for latency and throughput.
And constraints?
Constraints are exactly the config space we give them. Fair question. So what gives? So it goes back to the original question. Helion is just PyTorch. It's amazing. We have just these configurations. Hey, just find me the right thing for my objective metric, which is latency. Reduce my latency. What gives?
I mean, essentially, we have to figure out, does it even run on this specific hardware itself? If I'm running it on H100, am I making use of TensorFlow?
I'll make it even easier. Okay. Fine. Within the constraint, I've given you all the right configs. The code works on AMD's MI350 hardware or NVIDIA's B200 hardware, etc., etc. Okay. Have at it. Like, what gives? What is the bane of, like, let's say, think about, I don't know, if you guys are C++ versus Zig programming language.
The overhead, right? We're writing it in Python, right? So.
But it is doing this whole gymnastics of converting to IR and blah and blue. But finally, this is what runs on the hardware. So I think you had a glint in your eye.
Is it the search space is too large, so you can't figure out what the right pathway is to get to the optimal solution?
Search space is too large is the problem. It's you can't figure out is the other problem where it's going on forever. Okay, so what ends up happening is that's kind of like I think all of you had the right intuitions, but effectively the search space is so large that doing anything dumb like heuristic-based search is going to take you forever, literally overnight. I'm talking about like overnight. Yeah, you can argue, oh, I just do this once and can't I get away with it? Yes, you do this once, but once every time you have to save your Triton cache and all that nonsense, right? Yes, it's a pain, but it can quickly add up because the amount of code, like the number of layers you might have in your LLM is large enough, and then quickly you run into exponential search times. So that's really the punchline, right? So anybody can spot a mistake in this? That's true. So if you do a grid search, it takes hours and hours. I think I was pretty conservative here. It takes several hours. But if we have like some sort of intelligent search, which is what we're going to come to next, arithmetic error, I've not add like 42,000. Okay, so LLMs cannot generate optimal kernels like we realized, but LLMs can make intelligent mutations, which is just like basically they can generate diffs like cursor, etc. Like if you put enough work into it, LLMs can generate intelligent mutations that are relevant. Okay, so it seems like we have all the pieces of the puzzle, right? We did the research, we have brilliant ideas apparently, and I'm just joking. We don't know what those ideas are. We are only taking a guess that they're incremental. They might be incremental, they might be breakthroughs that we discard. That is the noise part of it, but at least we have a system which you can later on add guardrails to so that it doesn't go whack. But you can generate ideas. But then the important bit about this is the kernel optimization, especially if you want to deploy these things, right? That's the holy grail, right? You allow a bunch of LLMs to have at it, and they deploy next week. You have like the most brilliant set of optimizations on your models. Okay, so what gives? Autotuning search space, like we just discussed, right? It's prohibitively large, therefore you can't do any meaningful search. I like that it's so murky that you guys can't even read it. I can say whatever I want. I don't even have to read the slides, but all of this is relevant. Yeah, so what we ended up doing was used OpenEvolve and did a kernel evolve, which is a council of LLMs. We'll come to exactly how it works in a minute, but think of it this way. It's like the old, anybody familiar with like heard of genetic algorithms? Evolutionary algorithms, yeah. So everybody discards it. Actually, turns out my college bachelor's project, randomly, coincidentally, was trying to solve NP hard problems, or at least NP problems using genetic algorithms. I find it funny that I was so bad at everything then. I mean, I still am bad at a lot of things, but yeah, so we were not sure. Our code was so bad. There's this textbook, or not really textbook, but there's a book by Daniel Goldberg or something, on genetic algorithms. We just read that and we were like, okay, we know everything. So we started coding up in C, traveling salesman problem. The funny thing is, the genetic version and the textbook version, none of them ended. So we don't know if we did the genetic thing right or something else wrong. So it was funny. So for the longest time, it just was stuck in a while loop forever. So, but nonetheless, eventually we figured out a bug. So we presented a thesis, passed. But now, coincidentally, I was like, oh, okay, wait. Can LLMs do something meaningful, right? So what did we use? We used this evolutionary loop, fancy sounding things, but fundamentally same thing. You give it an initial meaningful seed, it generates a bunch of mutations, which is basically applies diff within a set of constraints, given a set of objective function. You evaluate it on real hardware, given a benchmark. That is the nice part about it. There are lots of tools that are coming up with these objective functions to evaluate things. So Optuna is another one, which is not really LLM guided or something. It just has a smarter backprop like gradient descent like search algorithm, which is very nice for very practical purposes. This is heavy hitting for large compiler backend and optimization. By the way, Google apparently claims to use this, not claims, they announced they use this, and they've found up to 1% or something ridiculous level of optimization, this being AlphaEvolve. They've not shared any code or anything of that sort, but they've shared enough details in the white paper, where they apparently have 1% at Google scale, 1% optimization of their cloud, like data centers, right? Energy utilization in data centers. They claim 37% speed up on attention mechanism using this. Yeah. So that is what got me interested in, like, okay, 37% on top of flash attention is like something. So let's try this out, right? Okay, evolution in action. So earlier, alpha tensor that I mentioned about, right, was very specific to gems. That's really if you have to take away one thing. Alpha evolve can generically explore mathematical functions, which is what allows it to be a tool in optimization for data centers, or we actually have it solves AMI. We have like AMI solutions, math problems, circle packing, a bunch of these other things with the help of evolve, which is awesome. Okay, so the evolutionary loop is basically, it has effectively like a bunch of phases where, I'll just get over this. Okay, it has like fundamentally a bunch of these, you get samples, either it could be initial seed, and then you build prompts to get the next generation of samples, and then you apply the diffs, which is why LLMs are so good at it, right? LLMs are good at generating diffs, not the whole things, whole kernel. And then you evaluate them on real hardware, and then you select the champions or winners for the next round, and then eventually, when you're tired of number of iterations, you just know if you want to stop or not. Right? That's really. Can someone tell me why can't we use backpropagation? Sounds like training.
What exactly?
So, okay, so the whole process, this evolution business, right? Here's some initial seed, random weights, yeah. Right? You see where I'm going? And then you build some prompts, and then you have some diffs, you apply the diffs, you try to run them, you benchmark them, you get the results, you select the candidate, and you apply it as a seed for next round. Why can't I replace this whole joke with backprop? It should be easy.
Backprop is C dependent, right?
C?
C dependent, like wherever you start.
Fine. Seed dependent, fine. I'll use the same seed, fine. But,
And what's the loss function? Like how do you locate it?
okay, go on.
I think that's the point. I mean, how do you?
Let's say in this case, we are expressing some loss function, right? We're saying, however we're selecting winners, I'm sure we can express it mathematically. Okay, minimum latency, maximum throughput.
Is your parameter space too large? Yeah.
We can limit that, fine, fair enough, but in this case, we are really like, what is the objective function at the end of it? We can control the objective function, really. Why can't we use backprop? Any of your brilliant minds. What is that?
Is there no ground truth?
Ground truth.
Ground truth for the back.
In this case, because it's so objective, like it's a fundamental like number, right? We're probably generating scalars. What is that?
You have a reward signal here.
Yeah. So it's a very definitive 0, 1, effectively. So why can't I use backprop? Backpropagation.
It will try printing on the seed itself and going towards the minimum rather than go at directions like sending that to a different space. So I should.
You could, but yeah, so why can't I do that? Exactly. Why should I not do that? What is it that is missing?
Are all your parameters like just numbers, pure numbers? Or
Sure.
number scale?
Yeah. Yeah. These are kernels, the configurations. Let's say I say, whatever, if it's like some strategy, I have some enums. Let's say I'm able to codify it into write tokens.
So usually,
Somebody said something, huh?
usually when genetic algorithm works, it has some new elements which are starting from a different position in the loss function. So if you're doing a backprop, it will start from one position and then just minimize on the local minima or like the minimum of that.
What's the mathematical word for it? I think you're saying it with a lot of words.
Usually when you use evolutionary strategies, it's when you can't differentiate.
Yes. It's
Worried about token minima?
no, it's a discontinuous function, right? Right? It's like, yeah, exactly. So you're right, right? So it's effectively, we don't know what the loss function even looks like. I can get a result from the loss function, but the function to determine how to get there is the problem. It's like some code. How do you express diffs? So that is when you want to use these weirdo, wacko, evolutionary, genetic, blah, 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 right? There's a lot of, like, it's heuristic plus plus, right? So you guys got it right. Okay, so I would have, all these are eye candy, but the thing is, I can show you the dashboard offline, but this is really how the dashboard looks, right? So what it does is, like OpenEvolve has matured enough, I recommend that you guys use it and tag me that you are using it so that I can be happy. The reason I'm happy is like, it's a fun project, that's it. The thing is, it gives you a very nice dashboard. This is literally a screenshot from the hackathon, so I've not really played around with it. As in, I've not really post-processed it or anything. So it literally gives you the code, the prompts, the diff. You can look at it, you can judge. If you scroll down in the diffs tab, you'll see what the diffs were recommended, what diffs were recommended by the Council of LLMs. So the nice thing is OpenEvolve is just open source project, so I recommend all of you just go contribute to it if possible. But there's like, you can have different LLMs of your choice, and all of them can, recommend. There's council of LLMs sitting there, and you go begging to them, and they give you this diff, and you come back and apply, and you evaluate, and you rinse and repeat. It's awesome, and it also gives you like a nice visual representation. You click on them, you find out, so you can visually look at the max or the min candidate and all that good stuff. So I recommend that you guys go play around with it. What did I want to ask? It'll come to me. It'll come to me. I forgot. But I'll share the slides, and I have the dashboard running, so we can look at it offline. I don't want to change tabs and stuff. It's awkward. Okay, so the traditional mutation, what I should have said earlier is, it's traditional mutation is random, right? LLMs at least understand that, oh, it's a language, it's a programming language. It's like Python, so I should not add curly braces somewhere where it's inappropriate or semicolons inappropriately. So that way, it's LLM guided evolution is better than the old school OG genetic algorithms. That's why I wanted to add it there. But it's still not enough, right? Oh, yeah. What is it that we are giving up here? What is it that we are using here? It's all it's all nice, but it can't be all sunshine and butterflies all the way. There's something that I'm giving up. What am I? Sorry?
Accuracy.
Okay, the stochasticity, but because the whole loss function itself is so weird, I'm okay with some amount of, the LLM saying inappropriate things here, which is really what stochasticity is, right? High temperatures, like, oh shit, it's blabbering. But what am I giving up here?
With every iteration, are you making like deterministic progress and stuff?
We don't know, but we don't need to. That's the nice thing about it. Ideally, we do, because the OpenEvolve, like through software guardrailing, we do, so that if there's a objective function that comes back that's shittier than the original, we don't even take it. Sorry. Yeah. So if it's worse than the baseline, we don't take it. That's it. We stick with the baseline. So ideally, we don't regress, but in spirit, there's nothing stopping us. We're just arbitrarily selecting.
But it's hard for an LLM to extrapolate, right? So given something that has been out recently.
Fair enough, yeah. But compared to Helion's auto-tuning facility, which is just heuristic, it just runs nicely on the local machine, what am I giving up here?
Yeah.
I could use any LLM, by the way. It's just any OpenAI API endpoint, I can give it, right? Or I can have like local LLM servers. I can just start my own SGLang, blah, instance with the model and have Quen, Coder, or Kimi K2, whatever. So what am I giving up? It's going to be the future currency. It's going to be the next Bitcoin.
Is it completely not compute?
Okay, like it's an analog to compute. What is it? Tokens. We're spending tokens. So the thing I wanted to open the door for you guys to think about is tokens will be eventually precious. We don't know how much of it's going to be commoditized, but it's also going to be a currency. So think of it that way, right? So I'm basically spending tokens. I'm asking the Shogat to respond to me, which is you get 3 wishes from the genie, right? So, so we're using that to evolve. Yeah.
Can you explain more about how does the mutation take place here? As in, are the LLMs reasoning around, that of all the mutations, this is how I should be?
I had a slide somewhere. Let me see. I had a slide somewhere. I'll show it to you offline. But basically, fundamentally, think of it this way. I give the LLM some code, okay? And I say, this is the current configuration for this PyTorch with a block size 64, tile size yada, 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 yada. I want to improve the latency of this, but my options are that. So that's my prompt, okay? So the LLM, we're still at its mercy. It can say, yeah, here's the C code, right? In theory, right? But the guidance we're giving it is through prompt as well, where now the LLMs are so good with generating code, and future they will be even better. So with that said, the mutations will be diffs or patches that can be applied on top of the prompted code, the candidate code. So that will be seen as the parent candidate, and then the diffs will be applied on top of it to form the child candidate, and both parent and child will be evaluated, and there's an internal data structure representation in the OpenEvolve software system that has a weighted edge from parent to child, saying, okay, there's a node worth traveling to, and so on. But fair question.
And are you giving it the history also of the previous runs?
Yes, in theory, good question, very good question. In theory, it can, right? So that it doesn't regress, but we kind of also can fall back on the objective function. We can say, don't mess it up any more than where it is. So ideally, if we have progressed to this child through the tree, through the genealogy, depends on how you have selected the future candidates. if you have added top k somewhere and you have randomized it, yes, you could regress, but not by much. That at least you can add some Gaussian noise to. All right. So very quickly, oh yeah, that's more than enough. Why did I want this? Oh yeah, so I forgot about it. AlphaEvolve claims to have solved some matrix multiplication gem problems in their internal system on TPUs. So why did I was going to go through this whole critical trade-off, tile selection, etc., but I'll spare you the trouble. But the idea is that this is not, like, it's hardware agnostic, it's system detail agnostic. It's this general concept that, evolutionary techniques, when prompted with the right way, but you're not adding the burden of syntax and semantics and runtime errors and pointer errors and memory misallocations and out of memory errors to the LLMs. If you remove that burden, which is really a majority of the kernel development, anybody who has written anything in any language, not even kernels, will know, right? So we're now cleverly, we're running away from the real challenge, but we're also getting to the destination that we want to get to, right? We don't care how we get there. We don't have to fight every battle. So we won't fight the battles we know we won't win right now. So we won't fight the syntax battle. We won't fight the semantic battle. So we'll run away from that, fine. But we'll get to the destination that we can achieve reasonable speedups within reasonable amount of time. And turns out there's evidence. Even Google says they have solved this for TPUs in their OpenXLA compiler ecosystem. So the trade-off is worth it. To what extent needs to be seen. There's more boasting about their gem optimization pipeline. I'll spare the details, but I'll share these slides offline. Or maybe I'll just write some blog or share the links with Saurabh. Let's see, what else did I have? Yeah, this was all about, So this is a team that we worked on the original kernel evolve. This is me. Sorry. We came fourth, but it was fun playing around with this. But the fact that we were able to get from nothing to a sort of a working solution within a few hours. This was not even the XAI hackathon. This was actually, we had even more compressed timeline for this. It was just the day to night. All these are super talented people who I just ran into in the event. Amin I knew from before, but nonetheless, still super talented people. So that's really what I wanted to share today. I think I have sufficient time for questions as well.